Okay, so now we're getting into it. This is the nitty-gritty. We have a complex circuit here. So I'm going to pause this video to draw this out. We've got a 9-volt battery, EMF. And we go up and we hit a 3 ohm resistor. And then in series with that, there's a 6 ohm resistor. We come down and hit this parallel branch. And in this parallel branch right here, we could go left across a 4 ohm resistor. We can go right, hit a 6 and then a 2 ohm resistor in series. And when it comes back together, we kick out and hit this 3 ohm resistor to come back to our battery again to complete the circuit. Okay? Now, what we want to know in this problem is what is the current and the potential drop across the 2 ohm resistor. So once again, what is the current and what is the potential drop across just this 2 ohm resistor down here? That is what we're looking for. So how do we go about doing this? Okay, so this one's gonna be a little longer. Buckle up, it's gonna be a good time. So let's start with this. We need to figure out what the current in this entire circuit is to begin with. I know I've got some total current coming out of here, right? We'll call this I1. And I know once this I1 hits this junction point right here, it's gonna split into an I2 and an I3. And I know this I3 is going through both the 6 ohm and the 2 ohm resistor, but I don't know what it is because I don't even know what I1 is yet. So how can we find I1? Well, let's go and use Ohm's law. We know Ohm's law is going to say that the voltage drop is going to equal to a current multiplied by some resistance. And if I can get the voltage drop across the entire circuit, 9 volts from here to here, all I need to do is figure out what is the equivalent resistance of everything in this circuit, and then I can get the total current here. So let's start by finding what is this equivalent resistance across the entire big circuit we've got here. Okay, so let's start with that. How do we find this equivalent resistance? Well, when we do equivalent resistances, it is helpful for us to start on the most parallel branch and then work from there. Okay, so let's start by looking at the parallel branch here with the 4 ohm and the 6 and the 2 ohm. Well, I can't just add in parallel yet because this 6 ohm and 2 ohm are currently bundled together. But I know that, if this is the 4 on this side, that the 6 and 2 in series are going to add together into an 8 ohm resistor. So I kind of have something that looks like this. Once I put the 6 and 2 in series, they're going to give me an 8. And now I can add this together. So I know that the equivalent resistance of just this piece right here of this parallel branch is going to be 1 over, because we got to take that reciprocal, and then it's 1 over 4 plus 1 over 8. And when I calculate this out, you want to be very careful. You want to hit 1 over 4, enter, plus the quantity of 1 over 8, enter, 1 divided by that answer. It's going to give us, just for this, 2.67 ohms. So that I know that this entire parallel branch setup can be thought of as just a 2.67 ohms. What I can do is I can say, look, the 3 ohms up here and the 6 ohms are in series. I can just add them together. 3 plus 6 is 9, plus 2.67, so that's going to give us 11.67, plus another 3 is going to give us 14.67. So I know that my equivalent resistance across this entire circuit is going to be 14.67 ohms. I had to do the parallel branch first, which meant that I had to do this little bit of series right here with the 6 and 2. Once I got that, I got the 2.67, and then everything from that point was in series. I could just add it together to get the equivalent resistance. With this equivalent resistance now, let's figure out the current in the circuit. So to do this, I use the Ohm's law. So I've got 9 volts, that's the whole circuit, equals the current in the circuit, we call that I1, multiplied by the total resistance in the total circuit, which we just found was 14.67 ohms. Do a little bit of division here. I divide the 14.7 on each side. We find that the current I1 here is going to equal 0.62 amps. So that's what our current is in this entire circuit. So I know at this point right here, I've got 0.62 amps. And that 0.62 is going to split up, some of it going into the left branch, I2, some of it going into the right branch, which is what we want. So how can I do this now? Okay, so let's kind of give this a redraw down here. I want to look just at that parallel branching here. This is the 4, this is the 6, this is the 2. And I know coming into it is a current of 0.62 amps. So if you look at this branching right here, remember, we want voltage and current across the 2 ohm resistor. What can I do here? Well, I need to somehow get inside of this circuit. And it's kind of a hard thing to do. I'll show you a cheater's way to do it at the end of the video. But what I could do is I could figure out a voltage drop from the start of the parallel branch to the end of the parallel branch. Because remember, the voltage drop from this initial point to this final point is going to be the same across either branch here. If I go across the 4 ohm side, I'm going to get the same voltage drop as if I go across the 6 and 2 ohm side. Same voltage drop. The 6 and 2 will have 2 separate ones, but put together, they will equal the same thing as the 4 ohm. Let's build our circuit. So how can I do this? Well, if I want that voltage drop, I know that a voltage equals a current multiplied by a resistance, right? And I know the total current setting up here. I know this total current. I could redraw this parallel branch resistor. I could redraw this like this. If I thought about it as just one resistor where we had some initial point and some final point, because that's what this is, right? These 3 resistors here could be thought of as just one resistor, one equivalent. I could then find the voltage from the initial to final. So what I'll do is I'll say, look, this voltage is going to be equal to the current running through it, which was this 0.62, so it's still 0.62 over here. And then what's the equivalent resistance of this? Well, we already knew that. That's going to be our 2.67 ohms from before, which means that our voltage drop across this parallel branch here is going to be 1.66 volts. Okay? Now, is that super helpful at the moment? Like, that doesn't give us our final answer because we're looking for the 2 ohm voltage drop and the 2 ohm current, but it is a step in the right direction. What we can do now is, because we know what the voltage drop is across our resistive setups here, we can do the following. We could say, hey, if I know the voltage drop is 1.66 volts, then this means that if we just look at the 6 ohm and the 2 ohm resistor, this voltage drop from here to here is the 1.66 volts. I also know what this total resistance is. That total resistance there between the 6 and the 2, since they're in series, is 8 ohms. Well, what is the current running through this then? Well, that's easy. V equals IR. And this will actually give us the I3 of that circuit we are looking for. So by doing this, I can immediately find what the current is running through too. So I divide each side by 8. I find that the current running through this branch of the circuit, what we called I3 before, is 0.21 amps. Okay? And it's the same for both the 6 ohm and the 2 ohm because these are in series. Well, if I now know the current that's running through this 2 ohm resistor, I can find the voltage drop across it. I'll know that the voltage drop across this resistor here is just V equals the current running through it, 0.21 amps, multiplied by the resistance of that component, 2 ohms, which is going to mean that our voltage drop here is going to be a nice 0.42 volts. And that gives us our final answer to this problem. If we wanted to find voltage drop on something else, we could say, hey, look, the voltage drop on 6 is 0.21 times 6. And we notice that it's going to have a larger voltage drop than this here. If we wanted to do this for the 4 ohm resistor on the left side, we would calculate the current running through it. We could go back to this idea of the voltage equals the current through the left side times 4 ohms, and we'd find that current on the left. If we did that, we would actually find that current to be about 0.42, 0.41. That'd be about 0.41, I guess. What do we find over here? Yeah, maybe about approximately 0.41 amps. Okay, if we did that for this current on this side, and then we can find the voltage drop across it. So we have to take these things like kind of one step at a time going through it. Okay, now I said I'd give you a neat little trick to kind of cheat on a problem like this. It's not really cheating, it's just understanding what's going on with your physics gut. If we think about this like we have been in regarding to currents as rivers, well, when we look at this parallel branch we had set up, I know that coming into it, I'm going to get 0.62 amps. Okay, that's what we solved initially. And I know that this current needs to break up. I know some of the current's coming this way. I know some of the current is coming this way. So can I figure out a ratio on where more current is going to go here? Well, I can. I can do this just by thinking about the amount of resistance. On the left side here, I only have 4 ohms of resistance, but on the right, when I combine the 6 and 2 together, I have 8 ohms of resistance on the entirety of the right-hand side. Well, here's the neat little trick. If we think about this, since 4 has less resistance than the 8, it's going to, 1, get more current, but 2, it's going to get a ratio more of that current. So the way we would solve this is, if the current coming in is equal to 1, the entirety, 100%, I can say that the ratio that the left side is going to get, or any branch of the circuit is going to get, is 1 minus, and then in this case, 4 divided by the total resistance we have. And when I say total resistance here, I'm just talking about adding them up. So 4 plus 8 is 12, okay? When you do this, you will get an answer of 2/3. We're going to get 2/3 of the total current to come on this left-hand branch. And if you take a look at this, and we kind of round it a little bit when getting numbers, if you take 0.62 and multiply it by 2/3, you're going to get 0.41333333. Okay? On the right side here, it's the same thing. It's 1 minus 8, that's the current, that's the resistance we have, divided by the total amount, just added together, 12. This is going to give us 1/3. 1/3 of 0.62 is going to be our 0.2066, which is rounded up for us to 0.21. Okay, so that's kind of like a cheater's way to do it for a nice parallel branch there. It works really, really well whenever you only have 2. When you start getting 3 and 4, it gets a little more complicated, in which case I would just go back to doing what we did here and actually working through everything. Okay, but if you've just got one parallel branch set up and you're just trying to like kind of cheat through a problem a little faster, you can find those currents faster by recognizing that the current has to split, and it has to split according to a ratio between the 2 resistances on each side. So that's kind of a quick way to do it, take care of a problem there without doing just a little bit more work. And really it wasn't a lot more work, we had to basically do one more equation, but if you want to get out of that and you can just quickly do ratios in your head, that's a nice way to do it. Okay, so a little bit more complicated of a problem, but nothing we couldn't handle. As you're doing more complicated stuff like this, it is just important to take it one step at a time. You'll notice how many circuits I redrew here. Pictures are super important when you're talking about circuits, and it's just take your time, work through it one step, and keep drawing things out so that you stay organized and you know what's going on. Okay, but with that, this problem here is finished. Let's get cracking. Let's go do some intergalactics. Till next time, adios.